applications to sampling. So first I want to thank Professor Kong and Yang to the invitations to give a talk here. So it's my third time to visit Korea, but still enjoyable, as Em said. And Wiener's lemma appears in many places as closely to the inverse problems, especially localized inverse problems. So I will talk about Wiener's lemma for infinite matrices and also its nonlinear extensions. So this is essentially closely to the inverse functions or nonlinear inverse problems. Then I will discuss some applications of the nonlinear Wiener's lemma to two nonlinear sampling problems. So both relate to the FRI signals. So this is a classical Wiener's lemma. It says that given a periodic function, if the function does not finish on the real line and has absolute convergent Fourier series, then its reciprocal also has absolute convergent Fourier series. So in some way, if the Fourier series has certain good property for its Fourier series, then as inverse or reciprocal also have quite similar property. So mathematically, if you write f as a summation of an and exponential of negative I n x, so that's Fourier expansion. And the Fourier coefficients, so this Fourier coefficients is summable. And if I assume that function is non-zero for every x, then its reciprocal, of course, is well defined because fx is non-zero, and 1 over fx is due periodic functions. So you can have periodic expansions, and the property you have is that the Fourier coefficients still is summable. So I will thank Vichari.
John on the right.
Yes, I also think that John has become taller.
No, you have to do it.
Looking down at me, I feel
You feel bad?
intimidated by
I choose that picture on purpose. Okay. So anyway, so thanks, Vichari. So I really get the idea of what's Wiener's lemma is important for the application of wave rates. Of course, I don't use Wiener's lemma to study wave rates, but for samplings. Okay. But anyways, it's important for me to get my attentions for the Wiener's lemmas. So this is my mathematical interpretation of the Wiener's lemma. Also, you can connect the Wiener's lemma with signal processing by filtering an infinite matrix, because any periodic function you can consider as the filters. But also you can consider as a matrix, because the filtering application to sequence also you can consider as in the time domains that with matrix applications. So f as all path filter is equivalent to say the infinite matrix has a bounded inverse on L2. So that's essentially you make the mathematical connections between linear interpretation of a non-zero property for the functions and also the inverse property for the infinite matrix. We want to extend that interpretations later. Okay, so now because we have the matrix interpretation of the filtering or periodic functions, then we can reformulate the classical Wiener's lemma in the following way. So if you consider this is algebra, so it's a class of infinite matrix generated by sequence. Given any sequence, summable sequence, you create infinite matrix. So you can see this top is the matrix and diagonal is the exact same, the A zeros. So if this class of matrix is Banach algebra, then we have properties that if a matrix is in that class and invertible, then its inverse is also in that class. So that's another way to understand the Wiener's lemmas. Okay, so this is the classical Wiener's lemmas. But in some applications, especially when I'm thinking about non-uniform sampling, so there's a lot of matrix. When you describe this, so you have a matrix like this. This is not on the diagonal is not exact same, but it's close to same. So it's A0, but it's bounded by something. So a matrix is not generated by sequence, but the matrix have certain off-diagonal decay properties. So this kind of matrix appears in spline approximation, also in the wave rate, then essentially is waved on certain levels. So all non-uniform sampling, and also this type of matrix also appears in the time-varying filterings. So then how to understand Wiener's lemmas? So the philosophy behind the classical Wiener's lemma is that for infinite matrix have certain off-diagonal decay, then its reciprocal also have same type of diagonal decay. So that's the idea behind the Wiener's lemmas. But the problem is how to understand the off-diagonal decay. So this is what we want to understand later. So the Wiener's lemma have been used in many places. Here I mentioned few topics like wave rate and time frequency analysis, frame, so differential operators, numerical analysis, sampling, control theory, and signal processing. So I know a little bit about sampling and signal processing, frame, but not others. So, but I know the papers on those topics. But let's give you some ideas about the class of infinite matrix which has Wiener's lemma. So this is the first class of infinite matrix, which now is considered as called or is called Jeffers class. So this class of matrix have all polynomial decay of diagonal decays. So you can see as on the diagonal, then it's just bounded by constants, and all diagonal, the distance to the diagonal is j minus jk. So it's decay of polynomial decay. So it says that if the matrix is in Jeffers class and is invertible, so that means have bounded inverse in L2, then its inverse also in Jeffers class. In some way, its inverse also has all polynomial decay. So this is the second type of matrix. So this now is called GBS class. So this class is the matrix is dominated by convolution operators. So H generates convolution operators. So it's summables. So it says that it's quite similar if a matrix in that class, GBS class, and is invertible, and also is inverse is that. This is a direct generalization of the classical Wiener's lemma, because if this is equal, Aij is equal to H minus J, that's a special case. So classical Wiener's lemma, this is a special case of these theorems. And the third class is really the very classical, is there to show the class. So it's have been used in many places. So if we forget this alpha, then this is summation of the lows. This is summation of column, then take a superman of the lows. So summation of the lows, then take superman of the columns. So that's the way to understand. But we need to have some ways there. Make sure this will be the, you have Wiener's lemmas. Otherwise, it will be not true. You can see the next theorems say if alpha is positive, then we have Wiener's lemmas. So in some way, the matrix have a little bit polynomial decay, then its inverse also has certain decays, the same decays. But if alpha is 0, that's classical show class, then the inverse is not necessarily have that properties. So you have to be a little careful to how to select the class of matrix. So also the fourth class I want to mention here is a little bit related to the harmonic analysis. So the matrix is dominated by another sequence, but this sequence is quite similar to what you have for the second class. It's dominated by sequence. It's a convolution operator, but this edge is radially decreasing. So previous one is just summable. This is decreasing. So it's a good issue for that. This class of operator is dominated by the maximal functions. So you have later a lot of stuff related to harmonic analysis or others. So also you can see that we can change a little bit here to the invertibility is not necessarily in L2. We can change to the LQ, even the weighted LQs. Because usually when you say the L2, in the classical sense, L2 is better because you can use Fourier transform. But now you are not talking about its translate invariant. So probably L infinity is better, or L1 is better. Then we want to find the inverse in L1 instead of find the inverse in L2. So in this case, also probably you want to consider a certain weights there, find the inverse in that space. It's much easier to check. So that's why we would like to have this class will be a little bigger or small, depends on the different applications. Okay, so I have a very short summary for what we have done. It's like I'm doing too fast. So we can see that we have you have two classes of matrices. So the first class of matrix could be the classical Wiener class, or the Jeffers class, or this is GBS class. This is Grochnik-Show, and this is Berlin class. So this third class of matrix essentially is a good class of matrices. So it's a very good one. And another class of matrix is really is not a good one, but it's easy to check. Look like all bounded operators on L2, or bounded operators on LP, or bounded operators on weighted LP. So we want to make sure this is a subclass of D. So usually it's a sub-Banach algebra. So if you use the language of operator algebra, so the Wiener's lemma essentially is say that if a matrix as in the good class, and you can find the inverse, and in D, so this means a big class, right? So if B is small class, right? Then the inverse also you can find the inverse in the small class. So that's the philosophy behind that. So also, if you want to use engineering language, is that you start from time varying filters. So if that time varying filters is all path filters, then it has local dependence. Then the inverse of that time varying filters is still time varying filters. But it's, that time varying filters also has local dependence. Of course, when we say local dependence, it's approximately local dependence. So Wiener's lemma has been used in many places, like localizing frame, and I think also in the numerical analysis, garbage systems, and all others. And also we want to discuss a little about the LP convergence. So usually when you do the numerical analysis, we just discuss about L2 convergence. Just because we have the Wiener's lemma, then we also can discuss the LP convergence. For P is different with T, because the matrix is a good matrix. It's possible to extend the convergence in L2 to the convergence in LP. In some cases, it will be crucial. We really need the L infinity or L1 convergence instead of the L2 convergence. Okay, so this is, we have said, is for the infinite matrix for, Wiener's lemma for infinite matrix. So Wiener's if in the matrix, you can consider, matrix can consider as a matrix and also a linear transformations. If you consider matrix as linear transformation, then you may think about how about nonlinear transformations. So linear transformations, that's what we have before in calculus. Essentially, is the functions. So you start from a number, then fx is functions. But for the matrix, this is the vectors. So of course, we can also consider x a sequence and fx also is a sequence. So now this is a nonlinear map. Or if you use matrix, then this is a linear map. So how about the nonlinear map? Do you have quite similar properties for the inverse of a nonlinear map? So if the map have certain local dependence, how about the inverse of the nonlinear map? Do you have certain type of local dependence? That's what we want to discuss next. So for example, this is the pictures. If you change amplitude, so change the amplitude, achieve the amplitude then with a sign. So this is the easy way to do it. So you change the amplitude. So it's quite local because you only change the amplitude. For every location, you can change the amplitude. For some application, we need that because for transmission, then probably you want transmitting these pictures. Then come back, then you want to restore the original pictures. Okay. So then, how to understand the relationship between the nonlinear map to the matrix? If you look at if fx is equal to ax is linear, how to get a from f? It's quite easy. If you take gradient of f, it becomes a. So a is a gradient. So that's the way to understand if f is linear. So then, in classical Wiener's lemma, we have something called off-diagonal decay properties. So how to understand to understand the off-diagonal decay property for the nonlinear map? So we can do that way. So we give a function, we take a gradient, but now the gradient is not constant. It's not constant. It depends on the locations. But the gradient of f is a matrix. So if you assume something about this gradients in some way, if uniform off-diagonal decay property, that could be the corresponding to the off-diagonal decay for the matrix. So that's the way for us to understand how to understand the dependence, local dependence for the nonlinear map. So, or you can see that when this gradient have uniform diagonal off-diagonal decay, that means the gradient is sparse because non-zero value essentially is on the diagonals, near the diagonals. Far away from diagonal is equal to zeros. And also, it's really also you can understand this is something called neighboring properties. If you look at f, you have components there. So then let's say f1. Suppose f1 depends on a variable x1, x2, x3, x100 is always dependent. But what that means is the gradients have certain off-diagonal decay. So this really means f1 depends essentially on x1, x2 up to x10, not x11 or others. Or fn then probably depends on n minus 10 to n plus 10. So not like x1 or that. So that's the way to understand as a uniform off-diagonal decay property for the gradients. Okay, so then how to understand, create the corresponding Wiener's lemmas. So if A have certain off-diagonal decay, then we classical Wiener lemma say the inverse also has certain off-diagonal decay. So how about nonlinear map? So then quite clear, you understand the off-diagonal decay property for the matrix. Replace that by the uniform off-diagonal decay for the gradients. So then we can think about that. So if the function f is strictly monotonic, so this condition essentially guarantee that the function is invertible on L2. And if the gradient of the f is bounded and continuous in certain class, for example, here I mentioned that it's a Jefferson class, but you can replace it by a more general class. So it's continuous, then it's inverse. The function is invertible, and the gradient also has the uniform of diagonal decay. So that's really, we can consider this is the corresponding nonlinear version of Wiener's lemma. So we call it nonlinear Wiener's lemmas. So why you want to understand this? So if you have nonlinear problems like this, giving X with nonlinear filters, that's what we have for the B. So ideally, we don't have noise epsilon, so then we just try to get X from B. But in the case you have a noise, then how to handle problems? So what kind of noise could be reasonable in a lot of applications? In image or single distortion problems, sometimes the noise is measured by LE affiliate norm, is not measured by L2 norm. So that's really the problems. So if you measure by LE affiliate norm, so is that possible? This reconstruction is stable. Of course, stability is measured in the LE affiliate norm instead of L2 norm. So we want to say that we show that if the function f satisfies certain property, this is strictly monotonic property, so that's the same assumption as what I had before. And if the gradient of f is good, so it's uniformly continuous in the Jefferson class, then the function can extend to invertible function in LP for any p between 1 and infinity. So that means if the function is, you can find inverse in L2, and also you can find inverse in L infinity. So that means the inverse process will be stable in L infinity. So as long as the system is good, so the nonlinear system have good properties, so it's very local, then you can do that. So we want to have, this is really the theoretical part of my talk. So I try to have introduce the classical Wiener's lemma, give the extension to infinite matrix. Then I want then study the nonlinear extensions. So this is the second part of my talk. So I want to apply that to signal processings. So we want to study two problems related to signal with finite of innovations. So we have two senior professors here, so introduce FRI. So Peter have give a good introduction on that. So, but in some way I don't like that definitions because it's not mathematical definitions. But and Peter have interprets that how to understand what that means, innovations. So for my language, essentially is certain parameters. It's time-related or location-related parameters. So, and of course, how to understand what's the parameter, what's the time-related parameters. So for example, for delta impulse, the location of delta impulse, that's the time-related parameters. The amplitude of that pulse, that's time-related. So that's the way to understand parameters. So that's a uniform spline. So the location of the nodes, the amplitude at that place, that will be the time-related parameters. So recover signal, essentially we try to figure out the parameters. So if you find the parameters, then of course you recover the signals because we know the parameterization of the signals. So it includes a lot of classical signals, for example, signal in Wiener space or bandlimit signals or functions in shift-event space or time frequency signals that's in the Gabor system. Then you have time frequency signals, and also signals in the producing kernel Hilbert space or Banach space or any other spaces. Also, okay, so then the problem is how to model FI signals, because if you want to have certain mathematics to play certain roles, you need models. So you know that this engineering definitions, we have something called freedom or time-related parameters. How to understand that? So that's my way to understand the parameters. So we believe that the signal is a superposition of impulse response of varying positions, amplitudes, and waves. So that's the way for us to understand the signal. So it's a linear combination of phi lambda and c lambda. So c lambda is amplitude, and phi lambda is impulse response of times of signal generated device at the innovation positions. We believe that at certain positions you generate a signal, then the linear combination. That's the FI models. But I want to say that it does not include all signals with finite innovations. That's certain types of signal with finite innovations I can study. So I try to model those type of signals and try to study that type of signals. Okay, so you can see that if you know that this is the position, the amplitude, and this is the spline. So this is really the parameters. So that's the signals. So that's the way to generate signals. But if you can't find the parameters, you can't find signals. So essentially, we try to find the parameters. Okay. So of course, we don't know the signal. We really only know the sampling data in some way. So how to get the sampling data? Of course, there's many different ways to find the sampling data. So the first type of sampling data we get is by the following process. So this is signal f. So you change the amplitude. So by apply the function f. So essentially it looks like this image. You change the amplitude. So the wideness. Then you sample it. So use average sampler. So that's the data you have. Then we try to figure out what the x is. So if we can find x, then of course you find signals. So this is the first problem I want to study, but this is quite clear is a nonlinear problem, because f is nonlinear. So this is nonlinear problems. But it's quite local, because you can see you change the amplitude locally. So you have the local property, but we want to recover signals. Okay, so, but in the classical sense, if you assume that the signal is band limited, so then you change amplitude, then you sample by band limited channels. Really, it's good because in this process, you can recover the signal edge from its data. So even in the middle part is nonlinear. And this band limit, this is the same bands. You sample it, you can go back. We just prove that it's 1-to-1. We don't have an algorithm to how to recover. But theoretically, we can prove that it's 1-to-1. Okay? So my interest on that topic really is related to Irina's work on signals in shifting event space. So I'm trying to extend his doubt for signal with finite of innovation in some way, or in general samplings. So this is my general average sampling process. It's in the middle. This is nonlinear process, and this is linear process. If we don't have this f, that's usually called average sampling process. So how to recover H from those data? Of course, you need to assume something about the signals. So that's our assumption for the signals. So the signal is living in this space. So the model for this is shiftless space. And also the other one is Fi signals, because if you change the generator, it's non-uniform generators, then this is essentially, this is my model for the Fi signals. So we have some technical assumption for that, like the space angle between space will be less than 1 or something like this. And also we need that the generator or every sampler is localized. Why we want to localize? We want to apply the Wiener's lemmas. Because if we don't have Wiener's lemma, we cannot find the inverse in LP. So it's very important to assume that the generator or sampler have certain localizations. If you have those localization property, then we have these stability properties. So in some way, if you know the data, you can recover the original signal, and also you have stability here. So the difference between data is the error between data is quite similar to the errors of the signals. So that's the stability. Also, we have the algorithm to recover the signals from the data. So we have an algorithm to that. So we have algorithm to convergence in L infinity norm or in LP norm. So it's not necessary for us to worry about the noise is in LP or in L infinities. So it's almost automatic. After noise L infinity, convergence in L infinity, noise in L2, convergence in L2. So also you can do the truncation or others that you like. So that's a good issues. But you can see that in previous slide also you can see that it's a little bit different with our normal Fi signals. For Fi signals, really a very important parameter is the locations. Usually the location length is unknowns. That's why we need a nonlinear process to figure out the locations. The unknown here for this theorem essentially is a C. The amplitude is unknown, but the location is known. So sampling process is nonlinear. Okay, so for this case, then of course, it's still very important to figure out what's the innovation, identify the innovation locations. So, but in general, it's very difficult. It's highly nonlinear process. We create new models for this or certain this type of problems. So this is quite similar to the shiftless space, but it's a bit different. You can see that there's sigma k there. So sigma k is unknowns, and also we want to figure out what the sigma k is. So usually we assume that sigma k is small. We don't care, But we need to figure out the sigma k and also ck's. So this kind of model, you can understand that signal are supervisions of impulse response of active and non-active generator device located as unknowns neighborhood of uniform grid. So you can this is uniform grid. So as unknowns neighborhood, but we don't know the location, but we know that as neighborhood of uniform grid. And also the device, you can see the CK, we assume that CK has a property like this. This means either CK is bounded and a typical CK is bounded. That means either 0 or is above certain numbers. So that means 0 is called non-active. Active then should be bigger than certain numbers. Of course, still bounded above. So that's the model for this type of signals. For this type of signal, it's possible for us to figure out the locations and also amplitude. That's what we want the theorem next. So we still have some assumption about the generators and the unsamplers. And we have this is a very technical condition, but this is really necessary conditions. After you have these conditions, then you can see the conclusion is that any signal like this with amplitude is not big, not small, and the location, in some ways perturbation is small and not far away from uniform grade, then you can figure out, you can recover from its every sampling data. If you know sampling data, you can figure out the amplitude and also locations. So this is nonlinear. So sampling process here is nonlinear, but the problem is nonlinear. So this is try to identify the innovation locations. But this is a perturbation of uniform grade. So it's still, in some ways it's perturbation, but it's perturbation in L infinity naught. It's not in L2 naught. Okay? So that's why we want to use Wiener's lemma in some way to do that. So you can see that if you start from signals like this, Ti is close to the I, but if you can replace Ti by I, the difference is like this. You can see a big difference. So if you really we can recover signals, then you can have perfect reconstructions. So that means perfect reconstruction. That means you can figure out the AI and Ti exactly. And also we have considered the noise issues or others. A little bit strange part here is that when you the average samplers, we don't use the audio samplings. We use the average sampler, and the average sampler will be like this, like square root signal of sine of the square root. So the reason for us for that is this function is not symmetric, it's not asymmetric, so it's a very strange issues. It does not satisfy strong fixed conditions. Really, in some way, it's a non-traditional average samplers. So you cannot assume, at least we can say that, our process does not work for traditional average samplers, for like splines, but it works for Gaussian functions. So Gaussian functions works, but they're not splines. Average from 0, 1 is not. So you have to not symmetric. So that's the general part. So this is how many time I have? I think that's just about 5 minutes. Okay. So this is a summary. So I can see that I have mentioned the Wiener's lemma. So this is art and work problems. So the art essentially is what kind of class. You have how to understand all diagonal decay. So this is art. It's difficult to appreciate. How to handle it. And of course, to prove it is mathematical issues. It's not hard. It's not easy. But sometimes it's an easy one. Okay. So and we have the nonlinear extensions, and also I have applied my nonlinear Wiener's lemma to two sampling problems. Especially, what I like is apply to identification of innovation locations, even locally. But that could be, at least for me, is a good step to understand nonlinear sampling problems. So here are some works, and most of my talks I can see found on the first papers. It's nonlinear Wiener's lemma and its sampling process, and also you can see a few of my papers on FI signals and or reproducing kernel space. And here are some papers on Wiener's lemma. So for infinite matrix or for integral operators or its application or others. Okay, I should stop here. Thank you.
Seems